In a lab in Denmark, scientists are building a computer out of a particle that doesn't technically exist. It's called a Majorana fermion, a ghost that is simultaneously matter and antimatter. And for 87 years, physicists thought it was pure theory. Microsoft just spent 20 years and billions of dollars betting it's real. And if they're right, it breaks the single biggest problem in computing that nobody's been able to solve. To understand the power we're talking about, don't think about a computer. Think about a team of chemists trying to design a new drug to cure a terrible disease. The problem is a protein that folds into a complex knotted shape. To stop it, they need to design a molecule that fits perfectly into that knot. Their supercomputer tries to figure it out, but it's like having a billion keys and only one lock. The computer has to try each key, one by one. It's so slow, it would take longer than the age of the universe to find the answer. The chemist will never see it. Think about what that means. Somewhere right now, there is a researcher who has spent her entire career, 30 years, hunting a cure she will never find in her lifetime. Not because she isn't brilliant, because the tool doesn't exist yet. This is where the quantum computer comes in. Its fundamental building block, the qubit, has a seemingly magical property called superposition. Imagine a spinning coin on a table. It isn't heads or tails, but a shimmering blur of both possibilities at once. That blur is the qubit's power. Instead of trying one key at a time, it can try 1,000,000, 1,000,000,000, all at the same time. It sees the entire landscape of the problem at once. For those chemists, that means finding the life-saving molecule, not in millennia, but in a matter of days. But this incredible power is born from an incredible weakness. The quantum state is the most fragile thing in the universe. A stray vibration, a whisper of heat, a random cosmic ray from a distant star. Any of it is like a finger flicking that spinning coin, forcing it to land before the calculation is done. It collapses, and the magic vanishes. This fragility, called decoherence, is the Achilles heel of quantum computing. The standard fix: build thousands of extra qubits just to babysit one. Google, IBM, the world's best engineers, they've all been pouring billions into this approach, and they've made real progress. But the fundamental problem never goes away. Microsoft decided to ask a different question entirely. What if you didn't protect the qubit from the world? What if you built a qubit the world couldn't touch? In 1937, a reclusive Italian physicist named Ettore Majorana theorized something that had never been seen, a particle that is its own mirror image, a perfect ghost, simultaneously matter and antimatter, existing and not existing at once. Physicists hunted for it for decades as a real particle. They never found it. But then someone asked, what if you could build one? The idea, however, didn't die. It came back in a new context, not as a particle floating in space, but as a quasi-particle. Quasi-particles aren't fundamental things themselves. They're like a wave in a stadium crowd. The wave moves around the stadium, but there's no single wave person running along the seats. It's the collective behavior of many people standing up and sitting down in perfect sequence that acts like a single entity. The theory was that under extremely specific conditions, a semiconductor, a superconductor, a precise magnetic field, all chilled to near absolute zero, you could coax electrons to behave together, creating these ghostly Majorana quasi-particles at the ends of a tiny nanowire. And that is exactly what Microsoft set out to do. Starting in the late 2000s, while much of the world was focused on making better superconducting and trapped ion qubits, Microsoft quietly began assembling a global team to walk down a different, much riskier path. They established Station Q, a collection of research labs, including a flagship facility in Lyngby, Denmark, one of the most advanced of its kind. Their bet was on something called topological quantum computing. It was a high-risk, high-reward strategy that some saw as an almost eccentric detour from the mainstream. The challenge was immense. They had to invent materials that had never existed, build custom refrigerators to hold temperatures a fraction of a degree above absolute zero, and operate in facilities cleaner than a hospital operating room where a single speck of dust could ruin everything. For 20 years they pursued this, a quiet scientific quest happening largely behind closed doors. Think about what it means to work on something like this. To spend a decade, your 30s, your 40s, chasing a particle most of your colleagues think you'll never find. To tell your family, at dinner, that today was a good day because nothing went wrong. The reason Microsoft was willing to take this massive gamble lies in a beautiful idea from mathematics: topology. Topology is the study of properties that don't change when you stretch or bend an object. To a topologist, a donut and a coffee mug are the same thing. They both have one hole. You can deform one into the other without ever changing that fundamental fact. Microsoft's idea was to apply this to a qubit. Instead of storing information in one single fragile point, like that delicate snowflake, a topological qubit would store it in the relationship between two separated Majorana particles. The information wouldn't be in either particle, but in their shared state, spread out across a distance. It's like protecting a secret. A conventional qubit is like writing the secret on a single fragile piece of paper. The slightest breeze can destroy it. A topological qubit is like braiding that secret into a long, sturdy rope. To read the secret, you have to look at both ends of the rope at once. A local disturbance, a gust of wind hitting one part of the rope, doesn't change the braid. To destroy the information, you'd have to physically unbraid the entire thing. The information is protected by the global property of the system. It would be, in theory, a qubit with built-in immunity to noise. That was the theory. Turning it into reality has been one of the hardest challenges in modern physics. For years, the field was filled with tantalizing hints and frustrating setbacks. Creating and confirming these Majorana modes in a real device is notoriously difficult. The signals are subtle and easily confused with other quantum effects. Then, in 2018, it all collapsed. A major paper, peer-reviewed, celebrated, the closest thing they'd had to proof, was retracted. The data had been misread. Years of work, questioned overnight. Inside the field, some began to wonder if the whole topological approach was a beautiful idea that simply didn't work in the real world. Microsoft kept going anyway. And then, quietly, the signals started changing. Not headlines, not press releases, just data. In a lab, in the middle of the night, looking different than it ever had before. Soon the announcements started. First, Microsoft presented peer-reviewed evidence that they had successfully created the topological phase of matter, the exotic, custom-built universe where these Majorana modes could exist. This was a critical milestone. They had built the stage. But the real promise of topology isn't just creating the particles, it's the stability they offer. The theory suggests that a qubit built this way wouldn't have a lifetime measured in millionths of a second. The target they are chasing is lifetimes measured in whole seconds, maybe even minutes. If they can get there, it's not just an improvement, it changes the entire game. It would be like upgrading a phone battery that lasts for a day to one that lasts for nearly 3 years. This claim is still emerging from the labs. It has to survive the brutal, necessary process of peer review, and the community remains skeptical until the evidence is undeniable. But Microsoft is confident enough that they have laid out an ambitious public roadmap, aiming for a machine that could start tackling commercially valuable problems within the next decade. And in a sign of the times, they're using new forms of AI to help sift through the immense data, accelerating the search for the novel materials needed to build these machines. Microsoft bet on a ghost for 20 years. The scientific community will now do what it must: test every claim, challenge every result. That's how it should work. But here's the question that actually matters. The first truly fault-tolerant quantum computer won't just solve one problem. It will solve the class of problem we've decided is unsolvable. Drop in the comments, what's the problem you'd hand it first? They bet on a ghost, a theoretical particle, hunted for a century, that could be coaxed into existence in the twilight world between matter and energy. At the frozen edges of a custom-built universe, the scientific community will, and should, continue to rigorously test every claim. But for the first time, it feels like a new path might be opening, a path to a stable, scalable quantum computer. The journey from a fragile, error-prone machine to a robust, fault-tolerant one has been the holy grail of this field. And it may be that the key wasn't to build a better cage for the storm, but to learn how to braid the wind itself. The question is no longer just how we build a quantum computer, but what kind of reality we will choose to build it from.